Good morning or good afternoon, grade 9s. We're going to get into our first topic on circle geometry, and the first thing I want to talk about is how to cut your birthday cake. So on your next birthday, if you have the option of cutting your own piece of birthday cake, this is maybe the most important thing you'll learn all year long, is how to cut a proper slice of birthday cake so you will get a lot of the cake. So this is what I recommend doing. If this is like a bird's eye view of your birthday cake, I guess it could be a square cake, but if it's a circular cake, you might want to do something like this. You blow out the candles, someone passes you the knife to cut the cake. This is what I'm planning on doing on my next birthday as well. I'm gonna make one slice right here, and one slice right here, and then there's the round part of the cake, and then I'm gonna have this huge piece of cake to eat. I'm gonna be so happy. And yeah, and what I've actually made here is something called an inscribed angle. Inscribed starts with the letter I, me. I'm very greedy. I want most of the cake for myself. Everyone else can just have these two little slices off the end. The inscribed angles are the very, very greedy cake type of people. And so this is a really important angle that we want to talk about this year. It's made by two lines that both touch the edge of the circle. In math and in circle geometry, those have a very special name called chords. These would both be chords, and the angle right here is our inscribed angle. It's the greediest angle of all. Okay, there's another important angle I want to talk to you about, and this is, maybe I'll just write this on the board. This black angle is our inscribed angle. The regular, well, not the regular, but another type of angle that we're going to deal with is called the central angle. And this is like your regular style of birthday cake. And so I'm going to use the same two endpoints. If I was to draw a beautiful straight line here and here, this angle here also has a very special name. Since both of those lines meet at the center, we're going to call it the central angle. Central angle, where both lines meet at the center of a circle. Now, both of these lines also have a very special name. They're both radiuses. Radiuses is grammatically incorrect. If there's two of them, we're going to call them radii normally. But each one of those lines is a radius. I can say that. So I got a radius here and a radius here. By the definition, any line coming from the center of the circle and hitting the edge of the circle is called a radius. And maybe I'll just throw this other new word up here as well, a chord. And the difference is between a radius and a chord is touching two ends of a circle. The radius starts at the center, goes to the edge. It's only hitting one edge here. Unless we're talking about a very special chord called the diameter, which is still touching both ends of the circle, but that line also goes through the center as well. Okay, now, the importance of both these angles is that there is a very, and this is one of the big, huge points of circle geometry, there is a very, very huge relationship between these two angles. if they are subtended by the same arc. And subtended is not a word that you're used to saying. Some of you may have never heard this word before in your life, subtended. So what does subtended mean? It means stands on. So both of these angles are standing on this exact same arc. And the fact that they are on the same arc is very important, because this relationship only works if they are subtended or standing on the same arc. We could almost like think of them as little dudes, where we have this guy and he is standing on this arc right here. This angle is being subtended by this arc. This little guy with his super long legs is standing on this arc. Same with this one. He is a teeny tiny little guy with really, really long legs, but he's still standing on that same red arc that you can hopefully see. And when they're both standing on the exact same arc, here is the relationship. Also, we will do this as an activity together so you can prove it to yourself on Friday in class chat. But for now, I'm just going to tell you the relationship, even though that is maybe not the best way to teach this. Normally, in regular school, we would do the activity first so you could discover it for yourselves, but that can't happen right now. That's okay. What we need to say is that, and this is the main thing, is that this central angle is always double the inscribed if they're standing on the same arc. So let's say this angle was 120 degrees. This one would have to be 60. The central is always 2 times as big if they are standing on the same arc. So in a lot of your questions, you're either multiplying by 2 or dividing by 2. Because you might run into something like this. Given this is 35 degrees, what is the central angle? And if you were able to grasp that idea just now, that the central is double the inscribed, you would double this angle to get this, and this would be 70, even though looking at the picture it obviously can't be that. That was a very poor choice of numbers, but hopefully you get the idea that the central angle is double the inscribed, and the inscribed oppositely is half of the central, whatever way you want to think about it. That is the main idea. Now, it might not always look so nice as the way that I have just done it, where the central angle is nicely over top. You might get something like this. You will get something like this in your textbook questions, where let's say we have this nice central angle of 100 degrees, and then they give us something like this. And it won't be in different colors like I just did. It's just going to be black lines, so it's going to be hard to figure out. But they're going to ask you for this angle right here. Or I'm going to ask you for it maybe on a quiz or a test or on an assignment. I'm going to ask you for this angle. So one thing that I like to do in circle geometry is I like to use a highlighter. And if I don't have a highlighter, you can do this with a pencil too. But what I'll do is, or maybe a pen of a different color, I like to either highlight or somehow bring out the important arc in this circle that is being subtended by this angle. And I just realized I forgot to tell you what an arc is. An arc is just a portion of a circle. little bit of a curvy line. That's what an arc is. And so the arc that we're dealing with here is this right here, this portion of the circle, because I have these two endpoints. So I'm going to go back to what I know. I have this arc being subtended by this angle of 100. This is a central angle. I have this angle being formed by two chords. Even though it looks kind of funny, one of the chords is super big and one is super small, that's fine. The relationship still exists. That this angle here must be half of the central. So I'm just going to grab Mr. Calci, punch in 100, divide sign, 2 equals, and this one must be 50 degrees. Gotta be. Okay, I'm going to show you one more special case and relationship that exists. And so, that's the case where we have a diameter. Shoot, it didn't perfectly go through the center of the circle, but let's just say it did. So there's our diameter, and another key fact that you will need to know, that you hopefully learned in previous years, is that there are 180 degrees in a straight line. So when I look at this straight line, it has 180 degrees in it, believe it or not. It is also subtending half of the circle, that huge arc right there, and I'm going to do this. Okay, so I have this triangle, and I want to know how many degrees are right here. Well, in this case, I have, even though it's a diameter, this is still a special type of central angle that's 180 degrees. I have an inscribed angle right here, and the inscribed has to be half of the central. And so half of 180 is 90. I can put this fancy little square there. And so where this comes into play is that if we can, in some of these triangles, or we have these different chords and a diameter up here, we might be asked to solve for given lengths. And the key thing is that once you see this little square here, it allows you to use something called the Pythagorean theorem, which was chapter 3 of last year. A squared plus b squared equals c squared. And so we will go through an example very shortly where we have to use that. Alrighty, let's just move on from here. And, oh good, there's my clicker. So hopefully you now know what a chord is, a line segment with both endpoints on a circle. We already talked about that. We have a central angle formed by two chords. It's the greediest angle of all, the inscribed. Starts with an I, me, I want the big piece of cake. Whoops, that was the inscribed angle. The central angle is formed by two radii and are meeting at the center. Ooh, the arc is just a small portion of the circle. We talked about that too. Okay, so a couple key ideas. Inscribed angles subtended by the same arc are equal. So that means this. If this is my circle, just a bunch of words up there. Hey, what does that mean? So if this is my circle and I have this inscribed angle and it is 30 degrees, if I have this other inscribed angle right here, and both of these endpoints are the same, they're both meeting at the same spot, all inscribed angles being subtended or standing on the same arc are the same. So this is 30. One more. I'm going to draw another inscribed angle right here with standing on the same endpoints, being subtended by the same arc. As long as these endpoints are the same, all of these inscribed angles are the same. They're all going to be 30. That was our first point. Central angle is twice as much as the inscribed if they're standing on the same arc. We already talked about that. And if we have a diameter, the inscribed angle is going to be 90. We just talked about that as well. So hopefully you now have a handle on all of our key ideas. Okay, let's take a look at two examples. Number one, point O is the center of a circle. So that's usually good information to know, because then we know we're actually dealing with a central angle and we can use that property. What are the measures of angles ADC and angle AOC? So when looking at angle ADC, and sometimes it might be labeled like this, with this funny looking L, that means angle, and then ADC. So when we're given something like this, and the way in math that we name angles is these are kind of like our the endpoints on our arms, and D is the vertex. It's kind of like the angle that we're actually measuring. And so if I'm looking at ADC, A and C are the endpoints and D is the vertex. So that means I'm looking for this angle right there at D. So in a way, the middle letter is the most important because that tells us where the vertex is. And so I'm going to use some of these circle properties to figure out that angle. So again, I'm going to go back to my strategy of highlighting an important arc. So I'm looking for angle ADC. I notice that it's standing on or being subtended by this arc right here. So is there any other useful information on this diagram? Well, I also notice this inscribed angle with the same endpoints being subtended by the same arc, and it's 52. So I'm going to go back to my key ideas and see if there's anything that helps. Oh, the first point right there. All angles being subtended by the same arc are exactly the same. So if this is 52, this is also 52. Didn't have to pull out a calculator or anything for this one. It's just 52. But we're using these circle geometry properties to prove this. Angle AOC right here. So I also notice that this angle is being subtended by the same arc. It's standing on that same arc, and it's a central angle. So I'm going to go back to the idea that the central angle is double the inscribed. I know that both inscribed angles are 52. Doesn't really matter which one I pick. So at this point, I'm going to double the 52. I'm going to take out Mr. Calci and punch in a 52. Then I'm going to punch in X and then a 2 and then equals. I got 104 as the central angle. So I'll tell you guys something that my geometry prof told me is that a lot of these questions are like little puzzles, and sometimes you just have to stare at them until the answer pops out at you. And yeah, but one strategy that you can use to help yourself is the one that I told you, is by highlighting or using a pencil and bolding that arc so that it'll bring out hopefully some inscribed and central angles that are going to be useful. Next up, example 2. Point C is the center of a circle. That's always important because now we know that we're dealing with the diameter up there. What is the measure of ADB? Okay, so that's an angle measurement here. What is this angle right here? Again, if it's D is where my vertex is, so I'm looking for this angle right here. Again, knowing that in a straight line I have 180 degrees. This is a central angle. I have an inscribed standing on that same arc. I'm going to take half of that, and this has to be 90. 90 degrees. And let's get rid of that. What is the length of chord AD? So what's the length of this guy right here? So typically, in these length problems, you'll be using the Pythagorean theorem, just as I talked about before, because we're dealing with a right angle triangle. And so, last year we looked at this theorem, proved it, did all the examples for it. So I'm just going to use it right now. I know you guys have already used it this year as well. So I have a squared plus b squared equals c squared, where a and b relate to the two legs of a right angle triangle, or the two shortest sides, and c relates to the hypotenuse, the longest side of a right angle triangle. So I'm going to do the longest one first because it's my c value. It is 5. So I'm going to put a 5 there, and that's squared. And the 3 is one of the legs, one of the shorter sides of the right angle triangle. It can go in for A or B. It doesn't matter which. Be careful. This doesn't mean 3 times 2. This means 3 squared, which means 3 multiplied by itself. So this is a 3 times 3. That's a 9. 5 times 5, 25. I want to get all my numbers to one side, to number nation. So I'm going to subtract by 9 on both sides. After I do that, I get b squared equal to 16. So b squared equals 16. What number multiplied by itself would give me 16? You might be able to do that in your brain. If you can't, you're going to take the square root of both sides to give you b equals the square root of 16, which is 4. 4. This length here is 4 cms. That's it. Have a wonderful rest of your day.